In this video, I'll show you how to create the famous simulation known as Conway's Game of Life. Now, this is a very interesting cellular simulation in which each cell you see on the screen has a few rules applied to it. I'll go through those rules in 1 second, but cells can either be recreated, they can die, or they can remain on the screen. This is a very interesting project that I'll show you how to build in Python using Pygame, not overly complicated, and you can finish this in under an hour or whatever the length of the video is. All of the code for this will be available in the description in case you want to check it out without actually going through the tutorial. Anyways, let's go through the rules of the game. Rule number 1 is that in a live cell, so the yellow cells you see right here, that have fewer than 2 live neighbors will die. Now that's due to underpopulation. Rule number 2 is a live cell with 2 or 3 live neighbors will remain alive. This is known as survival. Rule 3, a live cell with more than 3 live neighbors dies, and that's due to overpopulation or overcrowding. Rule 4, this is the last rule, a dead cell with exactly 3 live neighbors becomes alive, that's reproduction. Now with these rules, you can see that we get these really interesting shapes and patterns, and there's been all kinds of research and studies related to this game where you can create some really interesting objects. The way I've set it up here is that you can actually add cells onto the screen, you can delete them by clicking on them. We have a few keystrokes that I've added here that will automatically generate some cells for us. Really interesting project. I hope you stick around to build it with me. With that said, let's go ahead and get started after a quick word from our sponsor. Thanks to Taipy for sponsoring this video. If you're looking for an all-in-one solution for building and deploying web applications in Python, Taipy has you covered. Taipy is an open source Python library for building web applications. You can make the front end, back end, and deploy web applications with ease. Forget learning advanced CSS and JavaScript. Instead, use simple syntax to create multiple page dashboards and front ends with only Python and augmented Markdown. At the same time, Taipy is designed to build powerful and customizable data-driven backend applications. It provides components to organize and manage data through pipelines and data flow orchestration. Each pipeline execution is referred to as a scenario. Scenarios are stored, recorded, and actionable, enabling what-if analysis or KPI comparison. Taipy is designed to rapidly reduce your development time and provide all the functionalities you need to build and deploy entire applications. Get started with Taipy and their open source package from the link in the description. Alright, so as we get into the video here, I want to quickly go over the rules one more time in a graphical setting, just so everyone understands exactly what we need to do to implement this. So I've just pulled up a website that has kind of a great explanation here that you can read through. So pause the video if you want to have a look at it. But you can see that each cell with one or no neighbors dies as by solitude. And then each cell with 4 or more neighbors dies as if by overpopulation. Each cell with 2 or 3 neighbors will survive. And for a space that is empty or unpopulated, if it has exactly 3 neighbors, it will become populated. So it shows you a few examples here with the visuals. Just wanted to kind of pop that up in case you guys want some more explanation. Anyways, what we'll be doing is implementing this. The first thing we'll need to do is implement a grid system. We'll then need to add a way to actually add in these different cells and kind of generate them randomly. Then we'll start adjusting the grid by applying these different rules. Really cool what ends up happening here. Let's go ahead and start building this. Alright, so I've just cleared my Python file and we're going to begin writing this code. Now the first thing we need to do is install Pygame. Pygame is a 2D graphics library that we'll be using for this simulation. Very straightforward, you don't need to know anything about it. I'll explain to you everything you need in this video. So to install Pygame, we're going to simply type pip install and then Pygame here in our terminal. If you're on Mac or Linux, you're going to do pip3 install Pygame. If that doesn't work, I will leave 2 videos on the screen that will show you how to install Pygame. That's really all the setup we need. Now we can start setting up our Pygame window, which will be responsible for the simulation. So we're going to begin at the top of our program by importing Pygame. We are then going to say pygame.init. We're going to initialize the module so we can use it. We're going to start now by actually adding a few different colors. So we're going to say black is equal to 0, 0, 0. These are RGB color codes that we're going to use throughout the rest of the program. So I'm going to define all of the constants that we need at the top of the screen, and then as we go through, we'll kind of write the rest of the code. Next, we are going to have gray. Now, gray can be a bunch of different colors, but I'm going to go with 128, 128, 128. Again, the amount of red, green, and blue. That's what we're doing for the colors. Lastly, we're going to have yellow. Now, yellow is going to be 255, 255, 0. Whenever you're writing RGB, the maximum value is 255. The minimum value is 0. Okay, so now we have the three colors that we can use. Next, we're going to set up some dimensions for our grid and for our screen. So I'm going to say width, comma, height is equal to, and we're going to go with 800, 800. Now you can adjust this if you want, but I recommend you make it even numbers that are divisible by the next variable here, which is going to be our tile size. Now the tile size is the size of one individual tile. In this case, it will be 20. That means it's going to be 20 pixels by 20 pixels. If you want to make it larger, go ahead and do that. Again, I just recommend you make it evenly divisible by the width and the height so that it's a little bit easier or kind of looks better on the screen. Next, we're going to define our grid underscore width here. Now the grid width is going to be equal to the width integer divided by the tile size. This is just the number of tiles that we'll have in our grid. Remember, we're creating a grid, but we have pixels on the screen, so we need to kind of make the grid based on the pixels. Next, we're going to have grid height. Grid height is going to be the height divided by the tile size. Lastly, we're going to have an FPS. This FPS is going to be 60, meaning we have 60 frames per second. If you wanted to increase this, you can, but another variable again that we need. Okay, now that we have our constants, we're going to define a screen. Now the screen is where we're going to do all of our Python drawing or our Pygame drawing. So I'm going to say screen is equal to Pygame dot display dot set underscore mode, and inside a tuple here, I'm going to pass the width and the height that I want the screen to be. So this is how you initialize a new Pygame window. Again, you just pass the width and the height that you want inside of a tuple to this set mode. That's going to actually pop up a screen for us. And now what we need to do is create a clock and then implement the main loop. I'll explain this more in depth in a second, but for now we're going to say clock is equal to pygame.time.clock. And now we're going to set up what's known as the main loop. Now, whenever we're working in Pygame, we have an event loop or a main loop. This is something that's running constantly, that's checking for things like button presses, key presses, adjusting the grid for us, for example. So this is where a lot of the core logic will be called from. We'll separate it out into different functions, but we always have this main loop. So that's what we need to write first so that we can actually see something appearing on the screen, right? So what we'll do here is we'll define a main function where we'll place the main loop. For now, we're going to say running is equal to true. And then we're going to say while running, this is going to be our main loop. Inside of here, we're going to say clock.tick. And we're going to tick the FPS. Now, what this will do is regulate the speed of this while loop so that it only runs a maximum of the FPS times per second. So since we have 60 FPS, this means that this loop will run a maximum of 60 times per second. If you're on a very slow computer, it could run less than that, but this will make it so at maximum it runs at this speed so that if you have a really fast computer, like I do here, the simulation doesn't run insanely fast. Okay. Now what we need to do is simply handle an event when a user attempts to quit the screen or quit the game. So we're going to say for event in pygame.event.get. Now this is where you can actually loop through all of the events that have occurred since the last frame. So this will run 60 times per second and handle all of our different events. The one event that we want to handle right now is if the user exits out of the window. So we're going to say if event.type is equal to pygame.quit in all capitals. Then we're going to say running is equal to false. That will then stop this while loop from running. And then we will go down here and we will write pygame.quit, which will close the window for us. So as soon as the while loop is finished, we simply quit. Okay, that's great. Now we're simply going to call this main function. So we're going to say if underscore underscore name is equal to underscore underscore main. Then we will call main. Now, what this does is ensure that we are only going to call this main function if we are directly running this Python file. That's because you could be importing, say, a function, a module, a class, whatever it may be, from this file into another file. And if we were to do that without having this line, then it would actually start running the simulation. We don't want that. We only want to run the simulation when we directly execute this Python file, not if this Python file is imported by another file, okay? So now what we're going to do is go to our terminal, or however you want to run your Python code. I'm going to say python main.py, and notice a Pygame window pops up. It's 800 by 800 pixels. That's the width and the height that we set. And if we hit on the X button, it closes the window. That's what we implemented with this event right here. Perfect. The next thing we need to do is draw our grid. So what we'll do is create a function called drawGrid. Now inside of drawGrid, we're going to take actually a set of positions. Now, this will be a good time for me to kind of explain how we're going to go about actually implementing this. So what we're going to do is we're going to have a set, and this set is going to contain all of the positions of cells that are alive. Now we'll do this so that we can very easily access all of those positions without having to loop through every grid position when we're trying to update it as we go through and kind of perform the simulation. You'll see what I mean in a second, but this is very efficient because this means we only actually look where cells are alive and then check the neighbors around those cells, rather than looking at every single position in the grid where most of those positions will be unfilled. So when we draw our grid, we're going to draw our grid lines. Then we're going to draw the cells that are alive kind of inside of those lines, right? So essentially a bunch of squares will be drawn inside of the grid lines. Hopefully that makes a bit of sense, but that's kind of how we'll go about it. So with that said, we're going to go down here. We're going to say positions is equal to a set in Python, just so we have that defined. And now we'll go inside of draw grid, and we'll start by just simply drawing the grid lines, and then we'll draw the different positions. So to draw the grid lines is fairly straightforward. We're going to need however many rows and however many column lines we have going both horizontally and vertically. So we can start in any order that we want, but I'm going to start with my rows. So I'm going to say for row in range, and then the range of this is going to be our grid height. Now what we'll do is we'll draw lines for every single row that we have in our grid, right, which is the height of our grid. So to do that, we're going to say pygame.draw.line. Now the first argument to this function right here is going to be the screen that we want to draw the line on. So in this case, we want to draw it on our screen, right? We could actually have a subsurface or a nested surface, which is why this argument exists, but I'm not going to get into that in this video. Next, we need to define the color that we want to draw. Now we define the color in RGB. You can actually pass a string here as well, but I like to use RGB because it's more flexible. So I'm going to pass black, which is my RGB color code here for, well, black, right? 0, 0, 0. Next, you pass the starting position and the ending position where you want to draw this line. So the first position we want to draw this line is the following. Well, it's going to be 0, and then the row, so whatever row we're currently on in our iteration, multiplied by, and then this is going to be the tile size. So the way this is kind of going to work is when we're on row 0, well, we draw a line at the very top of the screen. When we're on row 1, then we're drawing a line 20 pixels down, right? Because we take 1 and we multiply that by the tile size, which is 20. And then on this side for the other position, we draw the line going to the entire width of the screen, which we have defined. And then same thing, row multiplied by the tile size. So the x coordinates are always staying the same for our line because we want to go from one side of the screen to the other. But the x coordinate, or the y coordinate, sorry, is going downwards as we draw, right? So we're drawing every single row. Now this would be a good time to mention that in Pygame, we use a 0, 0 coordinate system in the top left-hand corner of the screen, a little bit different than some other programs. That means that 0, 0 is top left, so as you go down, your y increases, and as you go to the right, your x increases. So keep that in mind, y increases as you go down. That's the opposite of a lot of other grid systems where y is going to increase as you go up, okay? So it's the opposite here in Pygame. All right, that's our row. And actually, before we go any further, let's just look at what that's doing. So we're going to kind of write a function here that says draw grid. We'll just pass it this empty position set for now. And if we run this the script here, so let's go and run this. Well, we don't have a background that's different than black, so we're not seeing any lines, but it should actually be rendering those lines. So what we'll do now is we'll change the background color. To change the background color, sorry, we're going to say screen.fill, and we're going to pass the color we want to fill this in. Now, I want the background color to be gray, so I'm going to say screen.fill gray. What this will do is fill in the entire screen with gray, and then draw the grid. Okay? Now, actually, that reminds me that one thing we need to do is we need to put this inside of the while loop, because I just realized it's not inside of here, hence why nothing is happening, and we need to update the display after we draw. Okay, so silly mistake there. We're going to say pygame.display.update inside of the while loop, which I messed up there. So now we fill the screen with gray, we then draw the grid line, and then we update the display. Whenever you want to actually take any of the changes or drawing events that you've done and put them onto the screen, you run this update command, and any of the draws that you've done will automatically be applied to the screen, okay? Now, these draws are also in an order. That means that if I fill the screen gray, and then I draw the grid lines go on top of the gray screen. If I did this in the other order, that means that I would actually go over top of my grid lines here, and I would not be able to see them because I'd be filling the screen after I drew the grid lines. Hopefully that makes sense, but that's kind of how that works. So if we run this now, you can see that we get our horizontal grid lines. The next thing we need to do is do the vertical ones. So the vertical ones are going to be the exact same thing, except just in the other direction. So let's copy this and let's change this to be for call in grid width. And now what we want to do is be drawing lines where we're changing the x coordinate, but we're not changing the y coordinate. So for the y coordinate, we're going to have 0, and we're going to have the height of the screen because we're always drawing from the top to the bottom. And what changes now is the x coordinate, where we say call multiplied by the tile size. And then we do the exact same thing over here. Okay. So now we've changed this just to be adjusted for columns. So if we go here and run this, you see that we get our beautiful grid. Okay, now that we have the grid, what we'd like to do is actually start drawing positions within the grid. And to be able to do that, we need to kind of be able to create these positions. So let's make it so that we can actually click down on the screen, create the positions, and then draw them onto the screen. Now, we can go in any order we want, but I actually will start by drawing them just so that once we actually get that code down for creating them, we can see them. So we have these positions. Now our positions are going to be in the following format: row, column, or actually we're going to do column, row. Okay, so kind of like X, Y. Now this is not going to tell us actually the pixel positions. It's going to tell us what kind of, position in the grid, right? So it's going to give us a column row in the grid, not the pixel location. So what we'll do is translate the column and row to the pixel location and then draw the position. So we're going to say for position in positions. Okay, so we're going to loop through this set. We're going to say call row is equal to position. So we're just kind of decomposing this into its two components. And now we need to figure out the top left-hand corner where we want to draw a rectangle kind of in this grid box. So whenever you draw something in Python or in Pygame, sorry, you draw it from the top left-hand corner. So I want to figure out the top left-hand corner of the grid box, the little cube, where I want to be drawing a square. So to do that, I'm going to say my top left is equal to, and very simply, we're just going to take the column and we're going to multiply it by the tile size. And we're going to take the row, and again, we're going to multiply that by the tile size as well. Now we're going to draw a rectangle. So we're going to say pygame.draw.rectangle. And to draw a rectangle, again, we pass the screen, we pass the color we want to draw it. In this case, it's going to be yellow. We're then going to pass an asterisk and top left, and then we're going to say comma, tile size, tile size. Now what we're passing here is a rectangle object. Now this asterisk will actually take the two different kind of objects we have here, the two different, what would you call these, elements, column times tile size and row times tile size, and it will just kind of write them out as if they were individual values inside of this tuple. I know this seems a bit weird, but this is called unpacking. So I'm unpacking the values so that they would kind of be written like this, right? Tile size, tile size. I know, seems a little bit weird, but just bear with me here. I wanted to show you a bit more advanced Python syntax in case you haven't seen that. It just treats them as their individual arguments inside of the tuple, not a tuple being passed here. Then I'm passing the tile size and the tile size, which is going to be the width and the height. So it goes the X, Y, width, height. And what you're doing there is specifying the top left-hand corner and then the width and the height of the rectangle you want to draw. Okay, so that's it. That will now draw the positions. If we want to test that, we can just add a position into the set here. So we can do something like 10, 10. And now if we go ahead and run our code, we should see a position appearing on the screen. We got an issue here. It says cannot unpack non-iterable int object. Okay, not sure why I'm getting that error there. It says row call position. So this is a bit of an issue. The way that I just put this inside of the set, it's actually treating each 10 as an individual 10, not as a tuple. Kind of annoying that that's the case, but we can actually fix this by just writing tuple like that. And actually, no, I don't think that's going to fix it. To fix it, we could do this, sorry. Positions.add. And then we can add a position like 10, 10. And now it will actually add the tuple. It won't just add 2 10s. Which is why we're getting that issue. So let's rerun here. And now you can see we have that position appearing on the screen. Okay, that's great. So now that we have that, the next thing that we want to do is we want to make it so we can click down on the screen and have a position appearing. So we're going to go inside of this event loop here. And we're now going to check for the event, which is the mouse button down. So we're going to say if event.type is equal to pygame.mouse button down, all capitals, no spaces. And this means you pressed any mouse, so like left, right, middle button, doesn't matter. What we're going to do is we're going to capture the position of the mouse, and then we're going to figure out what row column you pressed on, and then we're going to add a position for that. So we're going to say xy is equal to pygame.mouse.get_position. And now we need to translate a pixel position to the column and the row that you clicked on. To do that is kind of the opposite of going from row call to pixel, right? We're going to say column is equal to x integer divided by the tile size. And we're going to say row is equal to y integer divided by the tile size. Okay, so if we know every single tile is 20 pixels, if I'm at, say, 40, then I would be at position 2, 2, right? Because I'm in that second kind of grid. Hopefully that makes sense, but that's how you figure out what row column you're in. We're then going to say the position is equal to column row, like that. And now what we just need to do is first check if the position already exists in the set. If it does, that means that we're actually going to remove it, because if we're clicking on a tile that exists in the set, we'll just remove it from the set. If it doesn't exist there, then we'll add it. So we're going to say if the pause is in the positions. Another benefit of using the set is that you can look this up in big O of 1 or constant time complexity. And we're going to say positions.remove and then pause, another constant time complexity operation. Otherwise, we're going to say positions.add and then pause. If you're unfamiliar with time complexity, don't worry about it. My point is just this is much, much faster than working with an array, so we can support a much larger grid by writing code in this way. Okay, so there we go. We now will actually be able to press these down onto the screen, at least if I didn't make any mistakes. So let's bring this up and let's start clicking, and you can see that we have some positions. Now we can't click and drag. That would be a different implementation, but for now this is fine. Although it looks like when I press on them, it doesn't actually remove them, so we might have an issue there. Let's look at why we're getting that problem. So this is a silly issue, but I had is instead of in here, so that was never actually triggering true. So just change that from is to in. I was thinking like is in, but it's just in. My apologies there, guys. If we run now, you can see now we can actually remove our positions. Okay, great. So that is most of the user input handled. Next thing we'll do is just make it so we can clear the screen, and so we can randomly generate some positions just so we don't have to constantly write them out ourselves, sorry. So what we'll do now is we'll add another event down here, and we'll say if event.type is equal to pygame.keyDown, then we're going to check for a few different keys. Now the first key will be the clear key, the second key will be the generate key, and then we'll have the spacebar, which will allow us to pause and play the simulation. So actually we can go in a slightly different order. Excuse me here. We're going to say if event.key is equal to pygame.k_space. Obviously this is checking if you pressed the spacebar key down. Then what we're going to do is we're actually going to set a variable here called playing. We're going to make that equal to false, and we're going to go here and we're going to say playing is equal to not playing. Now all this will do is toggle this playing variable so that we are either pausing or playing the simulation. That's it. That's all that the space key will do. Next, we're going to say if event.key is equal to pygame.k_c. Notice this is a lowercase c this time. What we're going to do is clear the screen. To clear the screen, we're going to say positions is equal to a set. So we're just going to create a new set that will just remove everything that was in the existing set. And then we're going to say, sorry, that's coming a little bit later. Playing is equal to false. So we just pause the simulation after you clear. Lastly, we want to randomly generate a bunch of positions if you press the G key. Now you can pick whatever key you want for this, but I'm going to go with G. So I'm going to say if event.key is equal to pygame.k_g. Then I'm going to say that positions is equal to, and I'm going to call a function gen. Inside of gen, I'm going to specify how many positions it is that I actually want to generate. Now I want this to be random, so I'm going to say random.randRange. And this is going to be 2 to 5 multiplied by the grid width. Now, I know we haven't actually defined all of this yet. Just bear with me for 1 second. First of all, go to the top of the screen here, import random, so we have access to that random module there. And then we're going to make this gen function. Now, the idea is, again, I'm passing the number of unique positions that I want to generate, okay? So now we're going to go to gen, and we're going to write this function. So we're going to say define gen. We're going to take in a number, and all we're going to do is generate that number of random positions. To do that, we're going to return a set. Inside of the set, we're going to have a list. The list is going to have a tuple, and the tuple is going to say random.randRange. And we're going to pass 0 as the start index, and as the stop index, this is going to be the grid_width. And then it needs to be grid height. And then we're going to do the same thing again, random.randRange, and this is going to be 0 and grid width. Okay, and then we're going to say _in range and then number. Let me zoom out so we can actually read this. So how does this work? Well, what we're doing is we are creating a list here. This list is going to contain a bunch of random positions in a tuple. So what we're doing is using something known as a list comprehension. We're first generating a random position in the Y direction, okay? So for the row. So we're picking a random one between 0 and the grid height because that's all that's valid. Same thing here, we're picking a random one for the X position now between 0 and grid width. And then we're doing this for underscore. This is just a placeholder variable. You could put I here if you want, but since we're not actually going to use the variable, I'm just putting underscore in range and then number. Okay, so we're just creating this number of random positions for whatever the num is that we pass to this function. Now, why I'm converting this to a set is that what's going to end up happening here is all of these values here, they could potentially overlap. Now, a lot of times they won't, but it is possible that I generate the exact same random position. Well, I don't want to have duplicated positions, so we just convert it to a set, and that's going to remove any of the duplicates for us. Plus, we need a set anyways, so now positions will work, and if we press this key, we should actually generate those random positions. So let's give this a shot here and see. If I press G, you can see that it randomly generates a bunch of positions for us. If we want more of them, we can go down here and we can just kind of change these numbers around a little bit. So maybe 4 to 10, right? Because it's going to be random. Multiply by the grid width. And now you see we get a lot more positions appearing on the screen. Now, while we're at it, let's try the C key. Notice C works. It just clears the screen. And there we go. Okay. So now that we've done that, we want to start updating the grid. Now, updating the grid is not overly complicated, but it is kind of the most logic intense part of this application. So we're going to write a few functions here. First, this is going to be adjust grid. And what this is going to take in is positions, okay? And we're going to write another function here. And this is going to be define get underscore neighbors like that. And this is going to take in a position. And this is going to return an array or a set containing all of the neighbors of that position. Now, remember that what we're doing here is we're looking at every single kind of cell. And we're saying, okay, does this cell exist? Does it get deleted? And then if there's a cell that is not alive, we have to see, okay, should this become alive based on the neighbors of those positions? We'll go over the rules again, don't worry. And obviously we'll be coding them out, but it's important that for every single position we look at, we need to know all of the neighbors of that position. We need to know if they are an alive cell or not. And if it is a live cell, then we need to check, okay, how many live cells are you neighbors with? Based on that value, we either delete you, we keep you, or we potentially create a new cell in one of those neighboring positions. All right, so let's go to adjust grid. Now, again, the way we're doing this is we're only looking at positions that could potentially have any update to them. That means that I don't actually loop through the entire grid. I just loop through the positions which are live cells. So what I'm going to do is say all underscore neighbors is equal to a set. And I'm going to say my new underscore positions is equal to a set. Now, the reason I need this is whenever I make any updates, I'm making it based on the current frame or the current set of live cells. That means that I need a new set that I put all of my new cells into, which will exist at the next step. Because if I try to update the existing set while I'm kind of doing this update step, I could potentially kind of mess up how things are working, because I'm going to be deleting and adding cells, which will then change how the other cells react. I'm not sure if that makes sense to you or not, but I can't kind of make the update in the same position set. I need to use a new set for all of my updates so that those updates don't affect the other cells that I've yet to have a look at. Now, that's why we have new positions. Why do we have all neighbors? Well, the reason I have all neighbors is that I need to potentially check for the neighbors of any live cells if they should become a live cell, right? I don't need to check ones that are really far away that don't have any live cell neighbors, but any cell that has at least one live neighbor, I'm going to put inside of here, because then I'm going to check if it needs to become a live cell. Okay, so first what we're going to do is simply see if we need to delete or keep existing cells. So we're going to say for position in positions. Okay, and what we're going to do is get all of the neighbors of this position. So we're going to say neighbors is equal to get neighbors, and we're going to pass this position. We're going to write neighbors in 1 second, or that function. For now, though, imagine this gives us all of the neighbors. Now what I'm going to do is say all neighbors.update neighbors. What this will do is take this list of neighbors, and it will pass them all into this set. If any of those neighbors already exist, which is very possible, they will not be duplicated because they're inside of a set. So now that we have all of the neighboring positions, the next thing that we need to do is check if these neighbors are alive or not. Because what get neighbors will do for us is just return the coordinates or the row column of all of the neighbors of any given cell. So now we're going to do some Pythonic syntax here, and we're going to say neighbors is equal to a list that is filtered using the filter function. Now this filter is going to be quite easy. We're going to say lambda x, and we're going to say x in positions like that. And then we're going to pass here the neighbors. Okay, what did we just do? Well, I wrote what's known as an anonymous function. All this is doing is acting as a filter function. That essentially means that we're going to take this list of neighboring positions, and we're going to loop through them, and we're going to pass every single one of those positions to this function, so that they're going to be passed as the parameter x. We're then going to ask, is x in positions? So is this position a live cell? If it is, then we're going to keep that position inside of this filtered list. If not, we're going to remove it. So what happens is filter actually gives us something known as an iterator. We don't want that. We want a list. So we're going to convert filter to a list, and now we're good to go. That might be a little bit more information that you need, but essentially this just filters the neighbor positions and gives us only the ones that are alive, which is what we care about. So now we can say if the len of our filtered neighbors here is in 2 or 3, meaning it's equal to 2 or 3, just a shortcut to do that, then what I'm going to do is say new positions dot add, and I'm going to add this position. So all I'm saying here is, okay, well, if this position, based on the current positions, has enough live neighbors, so it has 2 or 3, then we'll keep it for the next round. So we'll add that into our new positions. That's it. That's all we have to do here. Now, if we don't add it, we are kind of implicitly deleting it, because, well, if we don't add it, it's not going to exist in new positions after this, right? Perfect. So that is it for kind of handling the positions or the cells, that we're going to be keeping or not keeping. Now what we need to do is see if there's any cells that we need to create, right, or that need to become alive. So to do that, we're going to say for position in all neighbors. So now we're looping through all of the neighbors of the live cells. That's why we collected them, so we could loop through them. Now we're going to say neighbors is equal to get neighbors of, and this is going to be the position, right? So now I want the neighbors of what were the neighbors of all of the live cells. I know, a little bit overwhelming, but that's what we want. Now, similar to this, we're going to filter this. I probably could make this a separate function, but it's fine. We're just going to copy this in here. So again, we're now going to look and say, okay, well, which one of these neighbor positions are alive? We're going to get all those, and then we're going to check the following. We're going to say if the length of neighbors is equal to 3, then we're going to say new underscore positions dot add, and we're going to add the current position, which will create a new live cell. Lastly, we're going to return the new neighbors, or the new position, sorry. Okay, so that's it for a just grid. We need to write the get neighbors function, and then we're actually pretty much done with this code other than just calling these functions and stepping through a few things. Quick, let's recap what I did, just because this is the most complex logic that we've had, given it's not that complicated, but you get the idea. We have all neighbors, right, storing all of the neighbors of all of the live cells from the current set of positions. New positions, this will be what is updated after we kind of run this whole update cycle. So this is what we'll see at the next step. Here, we go through all of the positions. These are live, right? These are the live cells. And we say, okay, let's get the neighbors of that live cell. This gives us all of those neighboring coordinates, right? So all 8 potential neighbors of that position. We're then going to say all neighbors.updates. We're going to put that in there so we can use them later. We're going to filter the neighbors so we only get the live cells. And we're going to say if the length of the live cells that are our neighbors is 2 or 3, then that's good. We're going to keep this position. That's it. Down here, what we're doing is looping through all of the neighbors now of the live cells. We're checking their live neighbors, and we're saying if they have exactly 3 live neighbors, well, we need to make this cell become alive. So we do that, and then finally we return new positions. Once we write get neighbors, this will put it all into perspective. How do we get the neighbors? Well, we have 8 neighbors, right? We have top left-hand corner, kind of top middle, top right, the middle to the right, middle right, or bottom right, I guess, bottom middle, bottom left, and then like the left middle side. You know what I mean, right? If you're looking at a grid, one position, you have 8 potential neighbors diagonally and horizontally and vertically. So what we're going to do is say xy is equal to position. Okay, so we're going to break this down because, again, remember, we're passing a tuple here that contains the column and the row. So we'll just denote that with xy. We're going to say neighbors is equal to a list. And we're going to say for dx in -1, 0, 1. This is one kind of more creative approach to get the neighbors. We'll explain this in 1 second. For dy in -1, 0, 1, and this stands for displacement in x and displacement in y. Okay, so continuing here, we are going to say if dx is equal to 0 and dy is equal to 0, then just continue. Now, the reason for that is that if we have no displacement in x and no displacement in y, then we're looking at the current position, which we don't want to look at. But the way that I'm writing this, we just need this little check here, okay? So we just press continue there, or say continue. Next, I'm going to say neighbors.append, and I'm going to append x plus the displacement in x, and then y plus the displacement in y. Now, again, notice we have -1, 0, 1, meaning that as we loop through this, we have 9 iterations. One of those iterations won't count, which is the center position. So all of those other 8 iterations will give us every single combination of neighbors, right? So we have like -1 in the x, which is moving left. And then that would be combined with -1 in the y, 0 in the y, and 1 in the y, which would give us all those positions to the kind of furthest left side. Then 0, okay, that's in the middle, same thing, -1, 0, 1. 1, that's to the right, -1, 0, 1. Okay. Only thing we need to do here is just make sure we don't handle a position that's off the screen. To do that, we just say if dx plus, or actually if x plus dx is less than 0, or x plus dx is greater than the grid width, then we will continue. And we'll copy this exact same thing, and we'll put this here, but we'll just check it with y, okay? So we'll say if y plus dy, or y plus dy is greater than the grid height. All right, just making sure that we don't have any positions that are going off of the screen so that we don't get any index out of bounds exceptions or any kind of issues related to that, or we don't end up generating the simulation that we can't actually see, which would be kind of silly. Okay, so now we have get neighbors, and we're going to return the neighbors list, and that is going to do pretty much most of the code that we need. Okay, so now that we have that, what we want to do is actually start calling these functions. Now, remember, we kind of have this pause state, right? I have playing, so either we're playing or we're not playing. Now, we also need to kind of keep track of what step we are on, or at least how often we want to update the screen. So we could update the screen every 1 second, every 2 seconds, every 3 seconds. You can kind of pick. But what I'm going to do here is say step is equal to 0. Or actually, this would be a better variable. We'll say count is equal to 0. And we're going to say the count underscore frequency, or really, we could call this update frequency is equal to 120. Now, what I'll do is at the very top of my code here, I'm going to say if we are playing, then my count plus equals 1. So this is saying, okay, if we're in the play mode, if we actually are activating the simulation, we're going to add 1 to our count. Now, that will happen a maximum of 60 times per second, right? So that means that every second, the count is going to go up by 60. So now what we'll do is we're going to say if the count is greater than or equal to the update frequency, which is 120, which means 2 seconds, then we're going to reset the count to be equal to 0. And we're going to say our new positions are equal to the adjustment of the grid passing the original positions. Because again, remember, this is returning new positions, which will be the new ones that we want to see. So we simply set our position set equal to those new positions that are returned from our adjusted grid function. There you go. That's pretty much all we need. A few other slight tweaks we can make. For example, if we decide to clear the screen, we can just reset our count. So we can say count is equal to 0 here, so that it's not kind of stuck at something. And lastly, we can just add a caption onto the screen here that tells us if we are paused or playing so that we know. So we're going to say pygame.display.set_caption, and we're just going to say playing if playing, else paused. Okay, so this is an inline if statement, and this will just allow us to, again, either show playing if we're playing or show paused if it is paused, so we get some feedback. Now, it's possible I made an error or two here, but let's zoom out for a second. I'll kind of slowly scroll through in case you guys need access to this. Obviously, the code will be available in the description as well. Okay, kind of there you go. Now, let's run this and make sure it works. Okay, so let's generate, and let's press the play button. Notice it says playing, and we should see that we start to get the kind of game running. And there you go, the simulation is running. Okay, so as we run the simulation, while it's playing, I can do things, right? Like I can remove them, I can add stuff in, I can kind of do whatever I want. I can press G and just have it like continue to go, right? And I can also press C and I can clear it. Just keep in mind that, you know, playing and pausing up here, it's kind of a little weird, like if you're generating while you're playing through it, but that works. You can do that. I set it up that way. Okay, so I think with that said, that's going to wrap up this video. That was actually a lot shorter than I thought it was going to be. And yeah, that kind of covers everything that we needed. So if you guys enjoyed, make sure you leave a like, subscribe to the channel, let me know if you enjoyed this simulation and you want more, and I look forward to seeing you in another YouTube video.